So everything we were talking about so far was all about two-sided limits, so now let's talk about one-sided limits. So our notation is changing ever so slightly, and it's down at that x approaches a part. So what we'll see here is x approaches a, and then there's this superscript, it's like an exponent, that's negative. And what that means is approaching from the left. So what this is saying is the limit as x approaches a from the left, so for values that are less than a, of f of x is, and I'm just using L with a subscript of 1 so that we can differentiate. So this is coming from the left-hand side, and then over here where we have limit with x approaches a, and now that superscript has a plus symbol, so that just means from the right. So this would be the limit as x approaches a from the right, so for values larger than a, the right of f of x is, and then we're just going to call that L2. So what's going to happen here is now we could evaluate problems that have that jump like we saw in one of the examples previously where that two-sided limit does not exist. Let me draw something similar here. So let's say we have our function increasing up to a hole, and then it jumps down below to a defined point, and then let's say it does something linear and increasing. So, and let's say A is where that jump is occurring. So at A we have this hole that's up above, and then we have this defined point down below. So if I was evaluating that limit as x approaches A from the left, what I would be doing is focusing on this part of the graph that has the hole, because approaching from the left, we would be focusing on the values that are lower than a. So I would want to be approaching from this left-hand side, getting closer and closer to a, and with that, we would be increasing up to that hole right there. So L1 would be occurring up at the top here, where that hole is occurring. But L2 would be occurring as we're approaching from the right-hand side. So as we're approaching from the right-hand side, getting closer and closer to A, we're going to be on the linear part of this graph here. So we'd be getting closer and closer to that defined point of our graph. So L2 would be occurring at that defined coordinate that was down below that started the linear part of our graph. So even though there's these kind of two different spots for A here, we can evaluate this left-sided limit and right-sided limit based on what is our function doing just to the left, just to the right. But keep in mind that if they don't line up, so like we have this jump here, that means that if we try to evaluate the two-sided limit, it does not exist. So that's this terminology down below here. In order for the limit as x approaches a of f of x to exist, so that two-sided limit to exist, both the limit from the left and the limit from the right must exist and have the same value. So if they approach the same value, then that two-sided limit exists. Okay, let's take a look at some examples here. So we're going to look at a piecewise function, and then we'll look at a square root function and evaluating these. Okay, so we have our piecewise function. So we're seeing x plus 1 for values of x less than 2, and then we're seeing x squared minus 4 for values more than or equal to 2. So we're going to evaluate the limit as x approaches 2 from the left. Let me just make a note here. So this is going to be from the left, and then we're going to evaluate from the right. So we're focusing on, oh, and sorry, there were units missing from this graph here, but right there is 2. So each box is a unit of 2. Okay, so we're really focusing on what's happening at x equals 2, but we have this jump here. So we have this hole that's occurring. Let's see, that function x plus 1. So we have something linear to the left of 2. So we're linear and increasing, and we're getting close to that open circle at 2, 3. And then it jumps to the quadratic, that x squared minus 4. So we have a curvature here of part of a parabola, starting at a defined point at 2, 0, and then increasing off to infinity. So if we're approaching from the left-hand side, so it's like we're evaluating what's happening at 1, 1.9, 1.9999. Like if we were making a table, we would be looking at these x values that are just a little less than 2, which means in terms of our piecewise function, we're using this x plus 1. So what we could do is evaluate this x plus 1. What happens if we plug in 2? So that would be 2 plus 1, which would be equal to 3, which is what we're seeing from the graph, is that our graph is linear and increasing up to a value of 3. So that left-sided limit is going to be that y value of 3. The right-sided limit, so here we're looking at like 2.00001, 2.01, all these x values that are just a little above 2. And with that, we're using the quadratic part of our graph. So it's like we would be using the x squared minus 4. So what we could do is evaluate it with direct substitution by plugging in x equals 2. So we'd have 2 squared minus 4, which is 4 minus 4, which is 0, which is the coordinate that we're seeing here, where we're getting that coordinate 2, 0 out. So with this, we have our left-sided limit, we have our right-sided limit. So let's say I asked us for the two-sided limit. If I said, what's the limit as x approaches 2 of f of x, without any negative superscript or positive superscript, if it was just x approaches 2, that's our two-sided limit. And because the left-sided limit is 3, the right-sided limit is 0, they're not matching up. So that would mean the two-sided limit does not exist. So I would go D, N, E. If we evaluated these and they were the same, like if they were both 3, then that two-sided limit would also be equal to 3. So wherever they're matching up, that would be the equivalent of the two-sided limit. But because we don't match up, it doesn't work. All right, one more example here. We're just going to look at the function, the square root of x. So what happens as we approach from the right, from the left, and the two-sided limit at 0? So our square root function, it has a restricted domain, so it starts at 0, 0, and then for the positive values, it kind of curves up and goes out that way. So like we would have the coordinate 1, 1, 4, 2, things like that. But we're not defined for any negative values. So approaching from the right, if we're approaching from the right, what we can see is those values are getting closer and closer and closer to that output of 0. So that right-sided limit would be equal to 0. The left-sided limit, notice if I try to approach this from the left, I don't have anything. I don't have any function to the left of 0. So even though we're defined at 0, 0, I'm having an issue there. So because we can't approach from the left, that limit does not exist. And this can often feel counterintuitive because we have a defined coordinate, but again, the limit is all about approaching. So if we go to evaluate the two-sided limit, so just based on these answers, so from the right we're getting a value of 0, from the left it does not exist, that tells me that the two-sided limit then is not going to exist either because those limits aren't matching up. Now we talked about direct substitution, and we could go and take the square root of 0 and see we're getting a value of 0 out, and that could make it look like there is a limit. But again, it isn't about the actual coordinate, it's about the coordinates around that value. So even though we are defined there, since we can't approach from the left, there's no limit right there. But we can approach from the right since our function's defined over there. But from the left, since there's nothing, that means that left-sided limit and that two-sided limit do not exist.